So we're going to solve some systems of linear inequalities today, and we're going to use a process called linear programming to find a minimum or maximum value of a linear function. And the function that we are trying to minimize or maximize is a function that's called your objective function. It's like your goal function that you want to maximize or minimize. For example, something that you might be trying to maximize is profit, and something that you might be trying to minimize would be cost. So how this process works is you have a system of inequalities involving restrictions on your situations. Maybe your factory can only get supplies to manufacture 2,000 iPads in a day, etc. And when you graph those inequalities that are your restrictions, you get what's called a region of feasible solutions, which encloses all the possible values of your variables that make your system be able to be true. And then the point that is going to maximize or minimize your function is always going to be one of the corner points or the vertices of your feasible region. To figure out which corner point is our solution, this one, half the work's already done for you. They've just given you the graph of your feasible region and your objective function. To figure out which of those values actually maximize or minimize your function, you need to plug the xy pairs into your objective function and see what the largest and smallest output you get is. So if I take each of my corner points in my feasible region and plug them into my objective function, I'm going to find out that my objective function is going to have its largest value when x is 5 and y is 6, and it's going to have its minimum value when x and y are both 1. So the previous one had the feasible region already graphed for you. This time we're going to do it the whole time through. So we're looking at a situation where Brad's trying to maximize his profit from his new newspaper stand. And my two variables that he has are the number of journals that he can stock and the number of globes that he can stock. So first I'm going to write my objective function. Look at your goal, maximizing profit. So my function that represents the amount of profit he's going to make, if it's 50 cents for every journal, is going to be 0.5x plus my $1 for every globe, y. Now I've got some restrictions. He can only fit 100 newspapers on his newsstands. So my constraints on my variables, one of them is if I add the number of journals and globes together, that value has to be less than or equal to 100. And then he also is guaranteed to sell 20 journals and 25 globes to regular customers. So it would be smart if he had in stock at least 20 journals and 25 globes because he knows he's going to sell them, and people might get upset if they don't have their paper available. All right, let's take and graph this set of constraints. So I already typed them in here. You might need to zoom out a little bit on Desmos to make sure you can see your feasible region. Mine's kind of that triangle in the middle there. I would like for it to let me tap all the points at once, but it's not going for it. So my corner points are 2080, 2025, and 7525. So for my feasible region, I've got my vertices, and then I'm not going to screenshot and put it in, but if you were doing homework or something, you could just screenshot that from Desmos and have it handy. The value of my objective function at each of those corner points is what I get when I plug those values in for x and y in my profit function. Now notice the objective function isn't part of your graph, by the way. It's just what we are plugging our corner points in from our feasible region after we graphed it. So 2080 gives me $90, 2025 gives me $35, and 7525 gives me $62.50. So not a real great income there for Brad, but his maximum income is $90. And remember, if you look at your original variables that we defined, x was journals and y was globes. So he's going to have a maximum profit of $90 by stocking 20 journals and 80 globes.